Thank you. So this is my last lecture, and so even though my lectures are about mean-field glassy system, what I would like to do today is try to go towards finite dimension. So as Gilles said yesterday, this is not easy, it's not something which is completed, but at least I would like to tell you at least the first step. So, okay, so from today, from let's say mean-field theory or infinite dimension towards finite dimension. So, well, I would like to start, even though Gilles already told you several reasons why, mean-field theory has to be corrected in finite dimension. So let me just, well, repeat again. So when you do usual mean-field theory for standard second-order phase transition, actually mean-field theory is pretty correct, meaning that, well, you know that there exists an upper critical dimension. Above this upper critical dimension, mean-field theory gets everything right. It gets, let's say, the qualitative property of the phase transition and even the quantitative property of the phase transition, meaning the exponents. Then if you go below the upper critical dimension, then, okay, the exponent change, but still, if you are, the global picture of the phase transition is correct. Now, in the case of the glass transition, if we do the mean-field theory, well, we get something in the limit of infinite dimension or within mean-field theory. When we go to 3 dimension, a lot of things change. Okay, so the status of mean-field theory is quite different from the one that you get for standard second-order phase transition. So going beyond mean-field theory is not something easy at all. So just to give you one example, again, Gilles give you already other example. So let's see one thing that I discuss a lot within mean-field theory is that there is this configurational entropy, S of F. Now we'll talk about where F is the free energy density, so as a function of F. This is what we saw yesterday. So S of F, F min, F threshold. So remember, if you are at a temperature which is below TD and above TK, you remember we discussed that we have a curve which is the configurational entropy between F min and F threshold. Now imagine that, okay, this we found within mean-field theory and is correct. And then remember what I meant by state. I told you that what I mean by state is if I put the system there, so remember, so in this space here, I have different pockets in configuration space. Each one of them, I call it a state, exactly like in the ferromagnetic Ising model, you have a state plus and a state minus. And a state for me is something that if I put the configuration here, then I have some stochastic, any kind of stochastic dynamics, which is reasonable. Then if I wait long enough, the system will equilibrate inside the state. And then, well, for all practical purposes, will be at equilibrium inside the state. And you will never jump out, okay? So like in the ferromagnetic case, if I start with the positively magnetized state, I stay there, okay? If I have a system which is large enough, because the barrier to go to another state actually diverges in the thermodynamic limit. Okay, so imagine that somebody come and say to you, okay, I did the computation for a 3-dimensional system, and I found this. And I found actually that there are many, many different states. There is an exponential number. Should you believe it? And actually, the answer is no. You can easily show that this is just impossible in finite dimension. It's not possible to have an exponential number of states, where states, I really mean, well, what I said before, with an S of F, which is like this. So let's just see an argument, and it's a nucleation argument. Since you saw it yesterday with Gilles, it will be particularly simple. So imagine that I pick one state, let's call it alpha, which is here. So it has a free energy F of alpha. Okay? And now, well, if I have this curve, there exist other states which have a free energy density which is less than alpha. Okay, so let's say here, for example, I know that there are states, and I can pick one which has F beta, and F beta is less than F alpha. This is the intensive free energy. So is it possible really to have two states which have a different free energy density? So Gilles say no, from exactly. So why is not possible? So imagine that. Let's say that we don't believe, and let's say that imagine that the state alpha is a real state. So if I put the system there, it will remain there forever. And forever means that I took the thermodynamic limit first, So, I mean, all the barriers that diverge in the thermodynamic limit are just equal to infinite, okay? And now what I wanted to show to you is that, well, it's not true. The system will go from state alpha to state beta in a finite time. And since it goes to a finite time, it means that alpha is not a state, because, I mean, it's just unstable. Okay, so how I can do it? So imagine that, I mean, again, the guy who gave it to me S of F, give me also what is the configuration, one configuration inside state alpha. I put the system there in state alpha. Okay, and then I let the dynamics go. So if I have a normal dynamics, what's going to happen is that in principle, I can nucleate inside the state beta. So imagine that state alpha corresponds to some particular arrangement of the particle, state beta corresponds to another arrangement of the particle. If I wait long enough, well, I can always have in the arrangement beta. It will be I will have to wait some time, but I can create it. Okay. Now the whole question is, once I have created this arrangement, does it go? I mean, is it going to disappear? So I get again state alpha, or this is going to invade the system? Again, let's think to be concrete to the Ising model. If the system is in state plus, of course I have droplet of state minus. But the fact is that this droplet will just disappear because, well, I don't gain anything in create a droplet of state minus. Actually, I'm losing a boundary energy, so this droplet will go away. And instead here, well, if I have a droplet here of radius r, so what is the difference in free energy to create when I create this droplet? Well, this delta F will be equal to, well, inside here I have state beta, okay? So what it means that, well, I will have F beta minus F alpha r to the d gain. This is a bulk gain. So because here inside the droplet, I have the arrangement which corresponds to state beta. So instead of having the free energy, intensive free energy F alpha, I have this intensive free energy F beta. So this is the bulk gain, okay? And then, well, maybe, yeah, exactly. It's a bulk gain. So this is a negative. It's a negative term. And then I pay something because here actually I put particle in some particular arrangement, which is good if outside I have state beta, but outside I don't have state beta. I have state alpha. So actually I'm going to lose something on the interface. And this is very general, but as long as you are in finite dimension, you have short-range interaction, this is what you should expect. And again, think to the Ising model if it is help you. If I have plus here and I have minus here, I will lose some interface energy. Okay? And so this will give me a term which is plus y r to the d minus 1. Okay? So this is the surface term, and this is the surface tension. And now if I plot this delta f, which Gilles did yesterday already, delta f is a function of r. So what I see is that when r is small, this is the term that wins. And this is a positive term, and when r is large, this is a negative term, and it's going to win. Okay? So for example, in 3 dimension, this goes like r to the cube, this goes like r squared. So if I plot this, what I get is something like this. Okay? And this value here, which is rc, r critical, tells me that actually if I create a droplet which has a radius which is, well, let's say, okay, less than rc, so actually I'm not gaining free energy. Okay? I'm still paying free energy if I'm here. Okay? But actually if I'm r larger than rc, actually I have a gain in free energy. And so, well, what the system is going to do, I mean, this you can prove it or you can just assume that it's okay. I mean, what the system is going to do is that it will, so the droplet will actually invade the system. It's exactly the same argument than the usual nucleation. Okay? So this tells you that, so this is going to happen on a finite time scale, okay? Which, well, is the time scale for nucleation that I think Gilles discussed yesterday. So this means that, well, it's not a proof, but it's an argument that shows to you that it's just not possible to have two free energy states with different intensive free energy. So clearly there is something that has to change here in this picture. Okay? Yeah? No, so, okay, so within mean field theory, they are not metastable. They are really true stable state because the barrier between them diverge in the thermodynamic limit. Exactly like in the ferromagnetic case, the plus and the minus are true stable state. And what happens indeed in finite dimension is that this state will become metastable. But what I wanted to explain today is, well, in which sense they become metastable.
And this RC is about the size of the barrier, or the
Sorry?
the RC is relative to the size?
So RC, I mean, this is just this is just an argument to show to you that the state alpha is unstable. It's not, I mean, I don't pretend that I'm finding what is the, let's say, the easiest way to make it unstable. I just show to you that just in this way I know that the state alpha is unstable. I'm not focusing on the let's say best mechanism to make it unstable.
It's unstable for R greater than RC.
Yes, sure. But yeah, it's unstable for R less than RC. But since I have a system in which I can run a stochastic dynamics, I wait long enough, I will always have a fluctuation with R larger than RC, and once I have it, whoop, it invades the system. Yeah.
I mean, if it's a random system, you can probably, this is probably the upper bound. You can probably optimize the surface area.
Yes, but I agree. But my aim here was not to find the best process, was just to show to you that the state alpha cannot really exist as a real state. There was another question? Yeah?
In ferromagnetic model,
Yeah.
Two states are very different.
Yeah.
In random model, two states can be very similar, so probably the surface tension is not very weak, probably.
Well, I agree. I mean, it could be that the surface tension does not scale like d minus 1, but I mean, the argument will go through anyway. So I mean, of course, if there is no surface tension, then I mean, there is absolutely nothing. You're right, it could be that the surface tension doesn't scale with d minus 1. Well, so in this case, well, okay, it will go more like this, but that's, yeah. Yeah?
This is a droplet with a bulk liquid, so what's the meaning of the interface between the droplet and the
No, and this is not within a liquid. If this is true, the state, I mean, here I have a state alpha, which is there forever. Okay? What I'm showing to you is that this is just not possible, and the system is a liquid. So this is the conclusion. I start to think that I have many possible arrangements that are stable. All these are different glass, and then actually I realize that this is not possible. The system is a liquid because it's going to nucleate the other arrangement. No? No. So within mean field theory, these are true states. So it means that, for example, the density profile is not flat. The density profile is like this, and it will remain like this forever. So it's a solid. It's not a liquid. And what I'm showing to you is that, well, I have a density profile like this in a certain state alpha. I have another density profile in state beta. But actually, if f beta is less than f alpha is not a state. I will nucleate the other, and I will go in state beta. And so I will move. So the system is actually, the bottom line is that the system actually here is a liquid. Okay, so, well, what this was just to motivate that we should understand something, because, I mean, mean field theory has, some serious problem, and we have to go beyond mean field theory. And so to go beyond mean field theory, well, it's not something that we know how to do completely, but we know something. And today I will tell you some of the things we know. Yeah?
So naively you could go down to F minimum and you get stuck there, and that's still corrugated density profile.
Sorry? So I say it again. So what's your point?
You nucleate down,
Mm-hmm.
until you hit F minimum,
Yeah.
then you get stuck there.
I mean, the fact, what I mean is that, I mean, the minimum can exist. I don't saying that you cannot have a glass transition, but just that you cannot have an exponential number of states. And indeed, I mean, now I come just to this, and now let's imagine that there is a glass transition, and let's try to understand it, but in finite dimension, starting from what we know from mean field theory. So again, I will use the ferromagnetic system as a guide. So in the case of ferromagnetic system, as I said yesterday, so you start with mean field theory, in which you have the Landau free energy, okay? But then, actually, what you want to study is more a field theory, in which the field is the local order parameter. So what you do is that you have your partition function, which is sum over all configuration exponential minus beta h of c. And then what you do actually is that you rewrite this in this way. You integrate over all magnetization profile, and then here you put a delta function. Okay, this is a functional delta function. Okay, so I mean, if I do this, I'm doing nothing because this integral times the delta gives me 1. Okay, but it's just a way to say that I write this like the integral, functional integral over all magnetization profile, and then I have exponential minus beta f of m of x, where this is the magnetization profile. Okay, so I mean, that's the idea of I have many variables in my system, but I know that there is another parameter. So in a certain sense, I integrate out all the non-interesting variables, and I have a theory in which I have just the fluctuation, the special fluctuation of the order parameter that I have to deal with. Okay, and so exponential minus beta f m, so f of m of x is defined, well, just using this equation. So it's minus 1 over beta, the log of the sum over c, exponential minus, sorry, there was a z here, minus beta h of c, divide, no, sorry, there was no zeta. Thank you. Delta m of c minus m of x. Okay? I mean, that's the standard thing that you do in, well, when you want to construct a field theory or when you want to go beyond mean field theory. Okay? Now, within ferromagnetic system, what is this f of m of x? So there are different ways to get it. So let's say there is the first way, which is, I don't know, if you are Landau, then you just write it. Okay, but we are not Landau, so I mean, especially in the case of glasses, we will have trouble to see what it is. So, but if you do Landau theory, this is what you do. So here you have a V of m, which is the V of m that you get doing mean field theory. And then you say, well, I have to consider that I have some fluctuation, and this I pay, the system will pay if fluctuates a lot, and so you put a gradient of m square. Okay, this is what, again, you do without doing any computation. Now, yeah. Thank you. Okay, so this is, let's say, first approach. I mean, in general, it doesn't. I mean, it doesn't work. It works again if you're a Landau. The other thing, the other possibility is there are different other possibilities. One possibility is, for example, for the ferromagnetic system, you can really try to do, I mean, this step exactly. Okay, the derivation of the field theory. I mean, not always you can do it. Sometimes you can, and so, I mean, sometimes you can do it exactly. Okay. Then, second possibility is that you try to do some, let's say, coarse graining. Which is, let's say, at the, which is within RG. So what you say is that, okay, I have my system, and then actually I consider that I divide the system in sub-boxes, where this is some microscopic length, and then I integrate over all degrees of freedom here, which gives me a certain m of x. Okay, this will be a certain x, here is certain m of x. And then I try to see what is the f of m that I get. Okay, this would be one possibility. In general, you cannot really do exactly, but you can give some argument. And then the third possibility is to study Katz model. So Katz model are model in which actually you have you have long-range interaction, but finite. And so this is actually a control way to go beyond mean field theory. Okay? And this is, well, it's another way that has been used, in which you can really justify this kind of m of x. Okay? Okay, these are three ways. I think you are for sure you have seen at least one of them in your lecture in statistical mechanics. Now we would like, yeah.
For Coarse model, is there any good reference on there?
Yes. So what actually about reference, I'm writing a full set of reference for my lecture. So I will put you, okay, both for let's say ferromagnet and then for glasses. Okay. So well, what we want to do now is to do exactly the same. So in principle, you know that when you want to study fluctuation on top of mean field theory for the ferromagnet. You start from this free energy, and then you look to the effect of fluctuations. And you know that, I mean, if you don't put fluctuation at all, so m of x is just a constant, so you forget about this term, and you get just mean field theory, which is the v of m that you get within mean field theory, which has the usual form like this. Okay? So we would like to try to do the same now, but for glasses. So, okay. Okay, so what you can do for glasses, well, now I'll do something that, in principle, one shouldn't do. So for glasses, we know what is the order parameter. We discussed it yesterday. Instead of m is the overlap q. Okay? So what I get is that, in principle, what I have to do for the partition function is always the sum over c exponential minus beta hc. But you remember what is the order parameter, is the overlap q, remember? So I can write it here. It was q of c equilibrium, and I can define it locally. So it's the overlap between equilibrium configuration that I took from the beginning, from the Boltzmann measure, and the configuration C on which I'm summing in position x. This tells me how much the two look similar at position x. And then what I can do, I just do exactly the same. So here I will integrate over, so this from now on will be a q of x. So well, okay, let's write it, you still write it like this. So I will just integrate over all field q of x. And here, well, I just replace. So here I have q, c equilibrium of x, and I want that this is equal to the field q of x. Exactly the same idea. Okay, so instead of getting this, I will have q of x here, q of x here, and here is always defined same way. Again, if you are right, if q is the order parameter, this is what we have to do. Okay? Okay, now the problem is that, well, there is no Landau, so we cannot, I mean, just say, okay, well, f q of x, we can just write it down what it is. So, well, maybe I write it on the other side. So what is f q of x? And how we get f q of x? So once we have f q of x, in principle, we have the field theory to study fluctuation on top of mean field theory. So, I mean, understanding what is the correct f q of x is still an open problem. So, and the problem is that, I mean, especially compared to the usual mean field theory, here you have C equilibrium, okay? So this means that I throw an equilibrium configuration, and then I want to know what is the theory of the overlap fluctuation with respect to this initial configuration. But this initial configuration is random, because I take it at random from the equilibrium measure. And so what means is that this f of q of x is actually a random function which depends on C equilibrium. Okay? I will come back to this later, or maybe I will tell you now. So in the usual, I mean, for ferromagnetic system, as I told you, you can think that you can divide the system in boxes. And then one way to think about the f of m of x is that within each box, while you have a kind of small mean field system and have some fluctuation of m of x, which are coupled via the gradient term. Now, what happens is that if I look now to the fluctuation of their overlap, now if we switch to the overlap inside one box, because the reference configuration, C equilibrium, fluctuates, so maybe here it fluctuates, and so it has a very, let's say, bad arrangement of particle for C equilibrium. And instead, maybe here it's very good. So what happens is that actually the V of Q, so let me write this way. If we are naive, and we are going to be, so we'll say that FQ of x is equal to just exactly the same than for usual Landau theory. Plus V of Q. And V of Q is the V of Q that we get from mean field theory. Okay, let's study the system between TD and TK. Okay? This will be our naive expectation. Okay? So I put it something here, which goes up. Okay? This is naive, because what I'm assuming is that the V of Q locally is the same. Okay? Instead, because the equilibrium configuration that I'm picking up fluctuates from here to here, so maybe actually here it's much easier to get a glass than here. And if this is the case, it means that the potential here that I have, actually the second minimum is lower. And here maybe instead, well, the disorder is such that it's more difficult. So it will be like this, for example. Okay? So you have local fluctuation. That, well, we don't know exactly. Well, I will tell you later maybe what we are able to do on this. Okay? But this was just to tell you that if we just try to follow the usual procedure and say, aha, FQ of X is like this, well, we are neglecting a lot of things. But what we are going to do is that we are going to do exactly this. So we are going to take FQ of X, which is like this, and we will see what we get. And then we will discuss, all the things that we left over. Yeah.
This suggests you want to add some random terms.
Exactly. But for the moment, right now, I don't add the random terms. I see what I get, and then I will say what is going to change adding a random term.
Although those I guess the original model is random. You have quench disorder?
No. Because the randomness, it just comes from the fact that the order parameter is defined with respect to an equilibrium configuration taken at random. So it's just one can do it for a normal liquid in which there is no disorder.
But that C equilibrium could be some jammed glass state, like that fell out of equilibrium, which is heterogeneous.
Yeah, it's certainly heterogeneous. In principle, I do it at equilibrium, so I pick it up from equilibrium. So for the moment, I'm just studying the thermodynamic transition, so I'm in equilibrium. Okay, so from now, so what we are going to study is the case in FQ of X. So let's say the functional that we have to study to go beyond infield theory is this one. Okay, but I wanted to warn you is that this is naive, and there is clearly much more to say. Okay, but let's take it. Are there questions on this? It's okay. You can tell me you're lost, or it's okay that FQ of X is like this. So physically, what it's saying is that V of Q, I have a certain V of Q which I compute from infield theory, and actually, well, I'm paying if I do if I have a profile on the overlap that fluctuates a lot. Okay. If you don't have questions, I go on. Okay, now what we want to understand is, I told you that this S of F is just impossible in finite dimension. So one could ask, is there a glass transition after all? So here we know that in principle we have a temperature which is Tk, at which within infield theory the system has a thermodynamic glass transition. Now what we want to address is, let's put some fluctuation on top of infield theory. Is there still a glass transition? Okay. So that's the question I want to address. Is there still a glass transition? At Tk. And I will address this question using this functional. Okay? Okay, so what I mean is there a glass transition. So what I should look for is there is a glass transition. So again, I will use the analogy with ferromagnetic system. So in a ferromagnetic system, a transition means that there is long-range order. Long-range order means that, so if I know that the system can be ordered ferromagnetically, so it means that it's mostly plus or mostly minus. It means long-range order, it means that if I take a system, a very big system, I fix the spin on the boundary up. This will fix the spin in the center of the box, which is 10 kilometers away, in the state plus. Okay? That is long-range order. There is information is transmitted very far away. And again, if I put all the spins minus on the boundary, then the spins in the center will be minus. Okay. Now here, in the case of the glass transition, if we just change, so what I have is that if I put the overlap, let's say very high on the boundary, what I should find is that the overlap is very high also in the center of the box. And what this means in words is that imagine that you give me a equilibrium configuration, so you give me all the arrangement of the particle, and then which looks disordered to you. Then what I do is that I take the box, I put the particle arranged at the boundary of the box exactly like in the picture you gave me, and then I look in the center of the box if the disorder pattern that I see is, well, the same of the picture that you gave to me. So if the system is order, if indeed, I mean, this disorder pattern is order, I should see the same, let's say, order structure in the center, okay? Which means that if I have a fixed and overlap which is 1 or very high on the boundary, I should have an overlap which is high in the center. Is it okay? Yes? No? Yes, for Gilles it's okay, but... Okay, so, well, this is the same. So what I want to do now is I do exactly this. So I will take, let's say, a big sphere of radius r, and I will fix the overlap equal to QEA, I mean, on the boundary of the sphere. And what is QEA? Remember, our V of Q is like this. And this is QEA. This is the overlap within the same, I mean, what within mean field theory is the overlap within the same state. Is the overlap that I see if two configurations are taken in the same state. Okay? So this is my condition. Q is equal to QEA outside. And what I want to know is, well, whether or not in the center I will get a high overlap, QEA. And I mean, whether the answer depends on the temperature and whether the answer depends, well, when whether I see that there is indeed long-range order when I approach TK. Okay? So in order to do this, well, the first thing that I'm going to do, of course, I mean, what I should do, remember, I have my partition function, which is the integral over dq of x, exponential minus beta f of q of x. So I should consider all the fluctuation of q of x. But the first thing that I will do is just I will minimize. I will look to the profile which are the most favorable one. Okay, with this boundary condition. Okay. So what I'm going to do, I want to find the q of x such that fq of x is minimized with the boundary condition, so in this geometry, and with the boundary condition, which is q of x is equal to QEA outside the cavity. And I mean, just to be simple, is because there is no it's simpler to derive all the things. I will consider the case in which r is much larger than 1, and actually so here we are very close to TK within mean field theory. So this here, so V of QEA, which you should remember from yesterday, is the temperature times the configurational entropy, is much less than 1, which means that T is, let's say, very close to TK. Okay. So, well, if I have to do the q of x that minimize fq of x, so what I have to do is I have to take just the functional derivative of fq of x, and then I have to impose this boundary condition. So let's do it. So the functional derivative of df dq of x, in principle, I think I can just write it down, because I mean fq of x is nothing else than the Landau free energy that you have already studied for the ferromagnetic system. So it will be minus the Laplace, minus c the Laplacian of q of x plus v prime of q of x. And then I have to impose that this is 0. I should look that, I'm looking at a minimum, and I have this boundary condition that has to be satisfied. And to have a life simple, again, here I have a sphere, so I have some radial symmetry. Okay. Don't hesitate to ask me questions if you are lost. Okay, so let's do it. So let's solve this problem. Well, okay, so let me see if I said everything that I wanted to say. Okay, so let's rewrite this equation using that I have radial symmetry. Okay, if I have radial symmetry, it means that Q will just depend on small r, where small r is the distance from the center of the cavity. Okay. So what I have to do, I have to write the Laplacian in radial coordinates, and this, well, I will write it for you. I mean, it's nothing difficult. It's plus d minus 1 divided by r d dr q of r. And then, well, actually, I bring the v prime on the other side. So I have v prime of q of r. Okay. And then I have the boundary condition, which is q of r equal to QEA when r is larger than, small r is larger than big R. And now, I mean, to solve this equation, now I mean, again, I'm simplifying, even though the result at the end is, is correct in general, but I'm taking big R very, very large. Okay? And since big R is very, very large, and what I will find actually is that Q of R will change close to the boundary. So this means that the regime in which, I have to study this equation is the regime which corresponds to R much larger than 1. Okay? And if R is much larger than 1, so this means that actually I can forget about this term. Okay? Again, I can do it with this term also, but the discussion will be a little bit more complicated, so I won't do it. Okay? So since we are working very close to TK, actually as you will see, we need only to consider very small r, big R, and so we have just to study this equation when small r is very much larger than 1. Yeah? No, because what I said is that Q as a function of R will, so okay, so I will tell you the answer, well, okay. Q as a function of R, you will see, it will be something like, let's say, QEA, and then, and then a drop. So this is big R. This drop arrives very, very close to big R, and it happens on a scale which is of order 1. Okay? So actually, well, the derivative here, the second derivative of Q of R is actually much larger than the first derivative of Q of R multiplied by 1 over big R. Okay? Okay, so this I can forget, and so I have the equation to solve, which now is much nicer. Q of R equal to V prime of Q of R. Okay? So now we have to solve this equation. So what reminds you? So if we have to solve it, did you see it already, this equation? Yes. Good. So this is just Newton equation for one particle in one dimension. And let me just make the translation. So if you call Qx the particle position, you call Rt the time, you call C the mass of the particle, and then you call, well, careful, here there is no minus sign. So this means that, actually, okay, now in the notation, let's say the V that I have here corresponds to minus V in the Newton equation. Okay? So it means that this is the equation for, let's say, write me, this is the equation for a particle. This is the Newton equation for a particle. Oops. In 1D, in an inverted potential. Potential minus V, okay? of Q in this case. Okay? Is it okay for everybody? Yeah.
Just a comment, there are problems more like this one, but I've seen in different contexts where you don't have to ignore the
Yeah.
that's like a friction term.
Yes.
You can
Yeah.
include it.
Yeah. No, I agree. I mean, this will be like a weird friction. It's like a friction term, and I agree. I mean, sometimes one has to consider it, but in this case, we can drop it, and actually we could keep it, but the computation will be more complicated. Okay, so now let's solve this problem. Everybody know how to solve this problem. So what I want to do. What I want to find is I want to find the configuration Q of x that minimize the free energy function Fq of x with the boundary condition that are here, and with the condition that R is much larger than 1. So what does it mean? So it means that now I have my mechanics problem in which I have a potential, which is like this, is the inverted potential. Here I have Q. And what I know is that at the initial time, so for me the initial time is when big R is, when small r is equal to big R, the particle is here. Okay? And I want to find a trajectory of the particle which is valid when big R is much larger than 1. And then I want to compare all the possible trajectory that I have. So there is a first trajectory, which is very simple, is, okay, if I start from Q, so Q of small r equal to QEA for any R, small r, okay? So this means that I put the particle here with 0 kinetic energy. Well, it's unstable, but, well, if I put it here, we remain here forever, okay? And this is the, let's say, the mean field solution. And this is going to give me, well, what kind of free energy value. So this solution verify the boundary condition and correspond to Fq of x. So C square grad Q square. So since Q of R is constant, well, this is not there, plus V of Q of R, but Q of R is constant, so I will put V of QEA. And since this is constant, I will just put out of the integral, and this will give you just the volume of the sphere, VQEA. Okay? And remember, always, VQA is nothing else than the configurational entropy. So this is very small. Okay. Okay, so now solution number 2, which is stupid one, and we are not going to consider it. So if I want a solution that is valid, let's say when big R is very, very large. So it's like saying I have a solution that is valid on a very, very large interval of time. So one possible solution would be I start with a little bit of kinetic energy, and then whoop, I will go down, I will go up, and then down again, and I come back. Okay? This is a valuable solution. Okay? In the limit of very big R, it's possible, because if I start with a very small kinetic energy, it takes a long time to escape from this, and then I go down, and then I go up again. So it's a solution in the limit of very big R. But, I mean, is it a good solution? What do you think? What if we compute the f of q of x in this case? What do you think of these two terms? What would we?
Very high.
The
first term will be very large.
So the first term will be high, and the second term will be also higher, actually, no? Because, well, remember, I mean, v of q is...
They're comparable.
Yeah.
Satisfy equation on both.
Yes, sure. They are comparable, but the fact is that I start from here, I go up, and then I come back. So actually, this term is not 0 in this case, and this term, the term that I have from here, is higher. Okay, so this solution, the fq of x, will be larger than the than this one. Okay, v of q of a. And by the way, physically, it really makes no sense. So I mean, if you think about it, so I mean, it's clearly we shouldn't take it. Okay. So, That will be,
You could nucleate bubbles like this.
yeah, this will be the,
Entropically, maybe.
yeah, I mean, there is a third solution which is actually the good one. So this solution, if one thinks to dynamics, will be the barrier solution, but I don't want to discuss this. It's the barrier between, so what I will find, I will find two minima, and this second solution is the barrier between them. Okay, so now let's look to the third solution, which is the physical one and the interesting one. Third solution, and well, so in the third solution, what I can do, I can start here with enough kinetic energy that I will go down, and then I will go up, and I will arrive here when, at the end of time, so when small r is equal to 0. Okay? It's enough, I have just to calibrate in a good way the initial kinetic energy. If I put too much kinetic energy, whoop, I will miss, and this will not be a solution. If I put too small kinetic energy, actually, I will come back, and this is not good either. So the best thing is I just have to put exactly enough kinetic energy to arrive here at the end of time. Okay? And so how much, kinetic energy I have to put?
To compensate the difference between...
Exactly. Exactly, because we know that energy in this Newtonian problem is conserved. What is the energy for the particle? Is the kinetic energy, so dq dr square. And then I have the configurational energy, and since the potential is inverted, it's minus v prime of q. Okay?
We are not quite solving initial value problem. We have two endpoints, right?
Yeah, exactly. Yeah, but exactly, yes. But I want to arrive here at the end of time, so I know energy is conserved. If I want to arrive here with 0 kinetic energy, well, I have to start with the kinetic energy here, which is just the difference. Okay? Sorry, it's not v prime, thanks. Yeah, sorry. Okay, so the initial kinetic energy is equal to V of QEA, which is, I remember you, T times the configurational entropy. Okay? And then what I have to do, I have to study, well, the profile that I get for Q of R when I start with a small kinetic energy. And this, so I will start here. Here I have big R. And so this I won't do it, because you can do it by yourself. It is just Newton equation in one dimension. But so what happens is that, well, at the beginning you have a little bit of kinetic energy. You are on an unstable point, so it takes some time to escape from it. And once you are at a finite distance from it, actually you fall down very quickly. Okay? So actually the Q of R that you get, the profile that you get, if you study this Newtonian problem, so it will be at the beginning I will change slowly. I will go down slowly. Then at a certain point I will go down fast, and then I will relax exponentially fast to 0. Okay? So this is Q of R. This is QEA. And here what I get is, here I have a certain length, okay, that I will call psi p, but which is not actually a big length. You can show that it goes like minus the logarithm of VQEA. Okay? Okay, it's not so important, I'm just telling you. Because you start with a small kinetic energy, you start to escape slowly, and then at a certain point, you go down. Okay? So, okay, now what is the free energy of this solution? So the free energy of this solution has 3 parts. So there is, if I look again to the free energy, well, I have an integral over dx, so I have to integrate within the droplet, and I have 3 different contributions. One which comes, let's say, from here, let's say contribution A. There is a contribution which comes from the when I integrate close to the interface, and then I have a contribution which comes when I integrate between this point where Q of R change very little. Okay? And now I want to get what is this F, what are these 3 contributions to compare it to what I found for solution number 1. Okay? Okay, so what are these contributions? So the first one, it's easy, is 0. Okay, so in this regime, Q is 0 and is flat, so I get 0. Okay, the gradient is 0 and the V in 0 is 0. Okay, now what is this contribution? So this contribution is just, I mean, generically, what you should think, how it's going to scale. So it can be computed exactly, but how it's going to scale will be a term like y, which is a surface tension, times like 4 pi r squared. Okay, I do it in 3 dimensions. Okay, why? Because I mean here I have a change on a scale which is of order 1, and I now have big R, which is, well, very big. Okay, so I just have to integrate this. I have just a contribution which corresponds to the surface of the sphere, and then I have a small term here, okay, which is the surface tension. And this y, you can compute it, and if you did the exercise that Gilles gave to you yesterday, let me write what is y. Is the integral between 0 and QEA of the square root of 2c vq dq. So you have to integrate v of q between 0 and QEA. Well, I think you have to take this, okay? But I mean, it's not, I mean, the precise value is not important, just to tell you that, I mean, one can compute it, and it's something which is of order 1. That's important, okay? Okay. And now we have the third contribution to do. Okay, so what is the third contribution? So f of c, so let me write in this way. So f of c is the integral over, so, well, roughly in this regime I have that q of r, it's almost equal to QEA, okay? So what's going to be? Well, it's going to be, well, I have to integrate 4p big R square dr vQEA, okay, from, let's say, R minus something which is of order, so it's R plus log of vQEA and R, big R, okay? I have just to integrate over this part of the cavity, and I have to put vQEA, okay? And so what is this? This will be 4p r cubed divided by 3 between, I mean, big R and R plus log vQEA.
It's an R minus, right?
R minus, where?
Sorry.
No, because there is a minus because V is small. Yeah. Times vQEA. So what is this? Is vQEA 4 pi divided by 3 r cubed minus r plus log v of QEA cube, which is equal to, let's say, remember that big R is very big. So at leading order, well, I just the r to the cube which is here will go away with the r to the cube which is here, and so what I get is 4p r squared minus log of vQEA. Okay? Okay.
Can you say again, where does the log come from? Log V.
The log here? No, I mean, or the log here. I mean, the log here comes from just the log here, and the log, I mean, you really have to do the computation to see that it's a log. But the fact that you have a certain length here that diverge when vQA equals to 0 comes from the fact that you start with a kinetic energy which is very small. So it takes time to leave the unstable point. And you have to do the computation to see that it's a log of v. Okay? Okay, so now let's compare the different contributions. So this is 0, and this one, look at this. This is of order 1, and this is r squared. And here I get something which is r squared, but in front of it I have v, which is going to 0. Okay, so the good contribution is this one. This is the leading term. Okay, so now we have the two free energy. This is the free energy for solution number 3. and then we have the solution, the free energy for solution number 1, and then we can compare them. Okay. Okay. Okay, so let's compare. So I have F1, which is equal to, for P R square, VQEA. And I have F3, which is equal to Y 4 pi R square. Okay? So what do you see? I mean, it's, well, if you compare the two, what's going to happen? So, I mean, VQA is very small. So, well, what means is that, well, so at the beginning, if R is small enough, actually, this is smaller than this one. Okay? However, no matter how small is V, if R is large enough, I get an R cube here, I have an R square here, this one will become more costly when R is very, very big. Okay? And when it happens, so when there is the, let's say, crossover between the two, is to a, so I will find it just equating the two, so it's 4 divided by 3 P R square C equal to, well, VQA equal to Y 4 pi R square. And so, and this will give me the critical radius at which the two are equal. And this one, so it's RC, that I will call it, okay, let's say RC is the constant times Y divided by the configurational entropy. Okay, or let me do it in two steps. It's Y divided by VQEA, which means that it's proportional to Y divided by the configurational entropy at temperature T. Okay. There was a question? Yeah.
So just, so this solution is some kind of a nucleation solution that's not a bubble, but it's an annulus or something?
So it's not, so what I'm not looking to nucleation. So I'm really forcing the boundary condition, and I want to see whether the boundary condition propagates inside. And so this will give me, actually this will give me the scale over which, on which scale actually I have long range order. So let me...
But I don't understand. So Q, by construction, V of QEA is higher than V at 0.
Exactly. So what I want to see is, in terms of, let's say, if it was a normal phase transition, is that I force the metastable state on the boundary, and I want to see whether the metastable state actually becomes stable if the droplet is not big enough. Okay, let me re-say what we found here. So what we found here is that if R is less than RC, when I take my system, I fix Q equal to QEA outside, I get Q equal to QEA inside. Okay? And instead, if R is larger than RC, let's say much larger, then if I fix QA outside, I will get 0 here inside. Okay? Q equals 0 in the center of the cavity. Okay? Okay, so this, now, does it remind you something that Gilles told you yesterday?
But it's an annulus, right? There's a region outside.
Yes. Yeah, there is this length that I call psi of P, which is here, but which goes like just, it goes like minus log of the configurational entropy. So it's much, it's much smaller than 1 over the configurational entropy. So it's, okay, so it's much smaller than RC. So you remember what Gilles told you yesterday? There was a length, very important length in his lectures. Yeah, so the point to set. So the point to set, what was the point to set? The point to set was, okay, I take an equilibrium configuration, I block the system outside the cavity, and I want to know whether or not in the center of the cavity I have the same kind of configuration, which is exactly what we are doing here. So we fix the overlap outside, and we want to know whether or not in the center of the cavity we have the same overlap. And again, think what it means having the same overlap. It means that if I fixed here the arrangement of the particle, starting from a configuration that is an equilibrium configuration that, let's say, you give it to me, then the arrangement here, even though it looks very disordered, will be the same, roughly the same up to small fluctuations. Okay? So what this means actually is that the system, and let me write it somewhere. No, so the conclusion is that the system actually presents long-range order on the scale RC. So what we found is that the system is what I will call amorphously order on the scale RC, which, as Gilles called yesterday, we denote like psi point to set. Okay? And this length diverge, so it goes like y divided by the temperature times the configurational entropy. So when we approach Tk, the configurational entropy, or V of QEA, goes to 0. So actually this is going to diverge when T approaches Tk. So let me again tell you what does it mean. So one, let's say, picture of this is that what it means is that actually your system, and this is of course is a caricature, but it's actually isomorphously ordered over this length, psi point to set. Okay? And so it means, yeah, if I fix, I know that, I mean, if I fix the position of the particle here, I will know almost exactly how are the position inside. But this length over which the system is amorphously ordered doesn't go, I mean, it's just a finite length. So the system, in principle, if I go very far, is not ordered anymore. Okay? So it means in a certain sense, and here it's, so I can just take on the question. So it's a bit of a simplification, but let's do the simplification. It means that if when I say to you, okay, I put the particle here, then I have to carefully choose on the particle how I put the particle here. Then I have to carefully choose on how to put the particle here if I want to reach a low energy configuration. Well, this is true up to a certain length scale. And after a certain length scale, actually, particle will be put in a certain way at random compared to how I put the particle here. Yeah?
Does that mean, like in an easy model, that there's domains of spins up and spins down? There are domains of...
No, I don't think there is. So this is, okay, so let me say what is, that this caricature has a name, and so this is called the Mosaic State. And it was introduced by Kirkpatrick, Tirumala, and Walliness, even though not computed in this way. So, by the way, this kind of computation, even though it was not done like this, was done for the first time by Silvio Franz. And what they did actually is more, let's say, it's a more phenomenological argument. But at the end, I mean, it was the same result. So so they did it before by phenomenological argument. So what they say is that, well, it looks like that the system actually, at the beginning we had the system within mean field theory. I don't know if I erased it. So within mean field theory we had many states. Then I show it to you that I cannot have all these states in finite dimension. And so what they say is that, well, actually, in reality I have states, but only on a finite length scale. So so I can have the state, let's say, alpha 1 here, the state alpha 2 here, and the state alpha 3 here. Okay? And so on and so forth. So in a certain sense, mean field theory is correct, but it's correct up to a certain length scale. And then on very large length scale, I don't have a well-defined state. Only, I mean, if I'm above Tk. When I approach Tk, the system is amorphously ordered on scale which are larger and larger. And then below Tk, in principle, there is a true glass transition, and the system is amorphously ordered over infinite length scale. So it's exactly like the ferromagnetic Ising model, in which, except that in this case, I mean, the position of the particle looks disordered to your eyes, but if you put it on the, I'd say, on the boundary of the box, and even if the box is 10 kilometers, while in the center, you will have a very well-defined position. Okay? Yes?
So at reasonable temperature, what is this length scale?
Okay, so let me so this is what Gilles said yesterday. So this, the point to set length. Okay, now let me just finish because I didn't answer the Patrick question. So this is a caricature. So what we know how to do is what I say to you. We put the overlap very high on the boundary, and then we know we can measure on which length scale we have that the overlap is small. So on which length scale the boundary is not forcing the bulk. This we can define, we can compute, and as Ludovic will tell you, I mean, we can even measure numerically. Now, this picture like this with alpha 1, alpha 2, and the interface is a caricature. So I don't think this is correct. And indeed, Peter Walliness, if you try, I mean, to say to him, I mean, come on, this is not a true description, he always say, yes, but I have to talk to the chemist, so I have to simplify. Well. But then when he talks to the chemist, then he say, well, all these physicists are just doing complicated things, but this is the true description. You know? So, well, okay. So, okay. So this is, well, this is okay. This is the important result. And so this point to set length scale, what Gilles told you yesterday, is that from what we know goes from 1 to, if you're really optimistic, let's say 5 at Tg. Okay. And then it depends on the liquids. In some liquids, it's even smaller. Okay? But as Gilles insists, the barrier depends on the length as the length to some power. And now I come back to this. Okay? So, I mean, you cannot dream to have a length which is 1,000. There is no way, except if you can have timescale which are more than the age of the universe. Okay? So, but let me comment on this now. Yeah?
You are talking about the middle point now, while we were throwing out terms because we weren't interested in the middle point, right?
What is the middle point?
What the middle? I mean, we are fixing the boundary.
Yeah.
And then we are talking about the middle point.
Yeah, the middle, or well,
right.
Anything in the bulk actually, far from the boundary.
In dynamics, we were throwing out terms because we were far away from middle point. Are those terms important?
No. All the terms that I throw away are terms which are which I mean it's. So, okay, let me...
In the dynamics over there, because we had one...
This one? Yeah, I mean, there is no... I mean, what you see is that I have this length, which is actually much smaller than RC. So this one goes like minus log of SC, and this one goes like 1 over SC. So it means that in my cavity, almost all the cavity has overlap 0. So actually it's fine, because all the dynamics is taking place close to the boundary of the cavity. So this is why it's okay. Yeah?
So these pockets are correlated, they have some kind of amorphous order inside them?
Yeah, so the...
It's different from the amorphous order the neighbors have.
Yeah, this is one way to put it, yes. In reality, again, there is no strict interface. So what you can say, another way to say it, I don't know if Gilles said, probably yes, yesterday, is that imagine that you give me a configuration. And then what I can see to see if there is some kind of order is that I can look if there are some patterns that repeats. Okay, in the Ising model, I know that, I mean, there is a pattern that repeats, which is all the spin are plus. Okay, if the system is ordered, in principle, as I told you, if I put the particle in some way here, well, this way, I mean, the way to put the particle on a larger length scale is fixed. So I can see whether pattern repeats, and the pattern will repeat over. I mean, I can increase the length scale, and then after a certain length scale, well, I will start to find, let's say, chaotic patterns.
So it correlates as you go away?
Yeah.
When you talk about spins, they are ordered. When the crystal is ordered, if it's disordered, how much more disorder or different in disorder could be to not be the one? So you said the pockets around it have different amorphous order, which is disorder.
Yes.
So,
but there is no strict. So there is no strict, I mean, it's not really that I have a pattern here and then a pattern which is completely different here, and then this repeat in some way. It's really, I mean, it's really a question of length scale. I mean, it's...
Yes, it correlates, but it's amorphous already to begin with.
Yes, yeah.
Which is uncorrelated
No. So let me give you an example. Okay. Well, I don't know if I can do the example. Okay, let's do the example like this. Okay, I don't know if I can do it like this. Okay, let's say I have this. This is a string. Okay, this string is order, right? It's 1, 2, 3, 4, because for you it's normal that it's order, right? So, okay, now imagine that I don't know. I will try it. I'm not sure I will be able. Etc. Okay? So at first sight, if you look to this, I mean, here it's normal for you that after a 2, after 1 there is a 2, after a 2 there is a 3, etc. So this is completely order. This one, well, after a 4, after a 5 there is a 4, well, it makes no sense. After a 4 there is a 7, makes no sense. But actually, if you start to look at this, you have 5, 4, 7, 8. Then I have 1, 2, 3, 4. And then I have again 5, 4, 7, 8. So I have pattern that repeats. The fact that the pattern looks random to you, well, it doesn't mean anything. It's just that we are, I mean, our brain pick up some kind of order looking at symmetries. So, I mean, the crystal, we can see that it's order. If it's something that looks disorder, we have trouble to see it. But
all these are not simple algorithms. Are they simple algorithms?
You can do it both ways. Either you, again, if you give me just one configuration, then I can see whether the system here is random or not, meaning that if pattern repeats. Another way to say it is that the configuration that you give it to me has a very low entropy if pattern repeats a lot. So it means that it's not chaotic, it's not random, it's very ordered. Okay, even if it looks disordered to your eyes. Yes.
So are you saying that as you near the transition temperature, you get these ordered puddles that grow larger and larger?
Yeah.
Okay. So then, if I look at that V of Q though.
Sorry?
I look at the shape of that V of Q.
Yeah. That one. Yeah.
Yeah. That's like the generic shape you get when
Yeah.
you have a cubic curve.
Yeah. Yeah.
Right? Which is like the caricature for any first order transition.
Yeah. Well, in this case, yeah, it's metastable with. Yeah. Right.
Yeah. So then this picture would hold for any first order transition.
No, I mean it's different. I mean it's so first in the so in a first order transition, when you do this, you are looking to a problem of metastability. Okay, in which let's say you have I don't know, a liquid and a gas, and then what you do is that you know that, I mean, if the gas is metastable, well, if at the boundary somehow I put a gas, I can make it stable if the size is small enough. Okay. Now what we are doing using the overlap is that the system actually, I'm looking to an equilibrium system, but I'm saying, okay, here I have an overlap outside which is equal to 1. So if I have force the position of the particle to be equal to 1 equilibrium configuration, so this will force the configuration inside to be the same. So it's, I mean, it's related. I mean, there is this relationship between glass transition and, let's say, first order phase transition, but you have really to make the translation carefully. It's not, okay? No.
I think I missed what you have to be careful about.
Yeah, because in one case, the magnetization is the order parameter. Here is the overlap. And the overlap is you have to compare one configuration to one equilibrium configuration that you took from the beginning. So it's a more complicated order parameter. So from what, I mean, what you get is different from what you get in a standard first order phase transition.
That didn't ever at all into this analysis. You just had some Q, it's whatever it is, and then you get it.
No, again, I mean, it's, I mean, if I, so in a, okay, let me say in this way. So in a standard first order phase transition, see if I'm here, if you give me one equilibrium configuration, the equilibrium configuration is here. Let's say that it's a liquid, this is a gas. You take an equilibrium configuration, and the equilibrium configuration is a liquid. You don't have any gas inside your liquid. Okay? Now what I'm saying is that if I take an equilibrium configuration of a supercooled liquid, thanks to our analysis, I know that within it, I have actually long-range order within a certain scale. So in that case, you have no long-range order at all. I mean, the system is just a liquid, and you don't have, I mean, you have no important length scale. Okay? Instead, in our case, we know that there are patterns that repeats. We know that the system is ordered over a certain length scale. And this is due to the fact that the order parameter is more complicated. It's the overlap between the configuration and an equilibrium configuration. Yeah?
So is it fair to say that in a snapshot, you just can't observe the order at all? You need to have this other information. That's where...
No, you can in principle. It's very difficult, but you can. So if you give me a snapshot, I can do this procedure, which actually was done, I think, on a hyperbolic plane, maybe, so it's not a real system, because it's not the good way to do it. Sorry. It's a nice system, sorry. So if you give me a snapshot, what I'm going to do is, okay, I'm taking a boundary, so I have my cavity, I look at the boundary of the cavity. Let's say that when I'm here, I see a certain boundary. And then I go inside the system, and each time that I see that I have this boundary, I look whether inside I have the same thing. And if the answer is yes, then I know that the system is ordered up to this length scale. And because actually doing, let's say, translational averages is the same thing of doing thermodynamic averages is the same. So you can do it in one snapshot. But if you do want to do it in simulation, that's not the good way to do it, except if you also put it on an hyperbolic plane. So, okay. So let me go on, because I would like to conclude. So, okay, so let me just recap from mean field theory. So within mean field theory, and this is to make a connection with what Gilles said, so if we have the temperature here, so here we have the dynamical temperature, here we have the transition temperature, and here we know that we have an exponential number of states. Real states, so they are stable forever. We know that actually the dynamics, so the relaxation time diverge here, okay? And so what we know here, if I plot the relaxation time tau as a function of temperature within mean field theory, so let's do mean field theory in blue, we get something which diverge at TD. And here I have TK. And why diverge at TD? Because actually in this regime, I have real states, and the barrier between the states, the barrier delta, scale like big N. Or if you take the infinite dimensional limit, we will scale like D, the dimension. Okay? So these are truly stable states, and the dynamic diverge here. Okay? Now in finite dimension, what we found is that, so this is mean field theory, and this is any finite dimension. So you see that, there is no upper critical dimension. This is any finite dimension. What I know, what we found is that actually here there are no stable states. But I have let's say I have I have amorphous order up to the scale. So for scale which are of order on the point to set. Okay? So and then what I expect for the relaxation time will be that, so the idea is that in this system here, actually, if you follow what I said before, the mean field theory is roughly correct on this scale, but then clearly is not correct above this scale. So one thing that you can think is that, when I decrease the temperature, the relaxation time first will start to increase because when I approach TD, there are some metastable states that are forming. So now the states are metastable. So maybe there is a first regime in which, I have that this mean field theory, the dynamics that you can see mean field theory is correct. But then I will cross over to something else, to another kind of relaxation. Okay, so I will have two regimes. One regime in which I have a dynamics which is, let's say, mean field-like, which is called the MCT regime, and that Gilles discussed, and they will be discussed by David Reichman. And then here I have, let me do it this way. So here I have barriers which are of order n. And here I have a regime in which the system, if you remember the cartoon, is order over a certain scale, xi point to set. So in this case, the system is order over all scale. So you have a barrier which goes like n. So what you can think, which was what proposed by Kirkpatrick, Tourmalin, and Wallines, is that in this regime, the barrier will scale like the point-to-state length to some power that I will call psi, okay? Well, in principle, well, you can put a reasonable value of psi, but you can be generic. You could say, okay, I have something which is really order over this length scale, so the dynamics will proceed to, I have to, when I change from one state to the other, and so this will cost me a barrier, and the barrier will scale in this way. And if this is true, then what I get here is that the point-to-set, I know that diverge like 1 over the configurational entropy, and which goes like 1 over t minus tk. And so the relaxation time, it goes like exponential over the barrier divided by the temperature, which means exponential of 1 over t minus tk to the power psi. Okay? So in this way, well, this is, you can, let's say, understand, or let's say, rationalize why you have, so first here, and then a dynamics in which the relaxation time diverge very strongly when you approach tk. Okay, so let me stress that what I told you, I mean, on the point-to-set is, I mean, can be worked out in all, completely in all, really in all details. Instead, I mean, what I did at the very end here, saying that I have a point-to-set, so I have a barrier which scale like the point-to-set to some power, this is really a phenomenological argument. So for the moment, there is no real, I mean, hard derivation of this result. Yes?
Get back to the term you neglected earlier on, the fluctuations.
Yes. Yeah, I come back. I come back now. Yeah. Okay, so this is what you get. And now I would like to tell you in the 5 minutes that remain is that, as Gilles told you, I mean, we are trying to go beyond mean field theory, but going beyond mean field theory is hard, because what you would like to do is put all type of fluctuation on top of mean field theory. And there are a lot of fluctuations to consider. So let's see what are the fluctuations that one should consider, at least the one that we know how to treat now, and then there are ones that we still don't know. And this will be, I mean, the first item of the list of things that I'm not telling you, but that have been done that are important in the theory of mean field glassy system. So first thing is fluctuations beyond mean field theory. So this is an active domain of research. And there is something that we are able to do and something that we still are not able to do. Something that we know that we are missing is the disorder. So the fact that the V of Q actually fluctuates from from region to region. And this is just due to the fact that we are comparing the configuration C with the configuration C equilibrium that fluctuates. So this actually will tell us this fq of x is a random function. And the most, I mean, what we are able to do and to, let's say, argue is that what should happen is that you have the term that I discussed, plus V of Q, but then you should also add a random term. And this random term is random because the initial configuration is random. And I mean, what you can think, I mean, an example of a random term will be, for example, the integral over d dx of h of x q of x, where h of x is a random field. So the average is 0, and then it's short-range correlated. Okay? So in reality, it's more complicated than this, but I mean, you can think that it's something like this. So you see that if you have a term like this, this will tilt the potential locally, because if h fluctuates, then sometimes the potential, I mean, the secondary minimum is put down, and sometimes it's put up. And now this is going to have effect, important effect, that we didn't describe. And there are 3 effects. So let's say in order of importance. The first one is that this length, which I call psi p, which is called penetration length, which is there, instead of going like minus log of v, it will go like 1 over square root of the configurational entropy. Okay? Well, this probably you don't care too much. Second thing is that if you try to study the property of the mode coupling transition, as I told you, the mode coupling transition or the dynamical transition is really a dynamical transition. I mean, it's a critical phenomenon, it's a dynamical critical phenomenon within mean field theory. So if you want to study the fluctuation related to this, if you want to study, for example, how chi4 or the dynamical length that was discussed yesterday by Gilles behave, it's important to consider this fluctuation. Third, which is maybe even more important, is now that you want to compare how big is delta. Because actually, if the delta is too big, is too strong, so this will destroy the transition. And this is like, okay, it's like in the random field Ising model. So in the random field Ising model, even though the system wants to order, so it wants to be in the state plus or in the state minus, if the external disorder is too strong, then, long-range order is destroyed. It's just because you have a competition between I want to be all up, and I have a random field locally that just tell me in a random way to point up or down. And here's the same thing. If this self-induced disorder, this disorder is too strong, the glass transition will be destroyed. Okay? Sorry?
Above 2 dimensions. Meaning
it's destroyed. Below 2 dimension is always destroyed.
So
exactly. Yes, and this is related also to what Gilles was saying yesterday. In 2 dimension, we don't expect a glass transition because of this. If there was no disorder, there will be a glass transition. Because of this, we are sure that in principle, there shouldn't be any glass transition in 2D. Okay, but this is just a part of the story. This is the story that we know, but still we don't know, if these are all the fluctuations that we should put. Okay, so actually, well, there are questions which are open, and I would say that there are 2 kinds of questions about, the role of fluctuation. There are, let's say, one which is completely theoretical, which is whether or not the fluctuation will destroy the glass transition. And this we don't know. There are people that believe, let's say, hope that it's not destroyed, people like Gilles that believe, no, hope that it's destroyed. But okay, there are no serious argument for the moment on one way or the other. And maybe Gilles actually unconsciously hope also that the transition is not destroyed. But he doesn't know yet. Okay? Then there is the question is, okay, who cares about the glass transition at TK? Actually, what you want to explain is what happened well before. So when you are close to TG, at which the length scale is of order 5 or 3 or 4. Okay? So maybe the glass transition is destroyed, but if all the slowing down of the dynamic is produced by something which is, by this physical mechanism, so it's the slowing down of the dynamics is due to the fact that the configurational entropy is going down and that the barrier are going up, even though this point to sect is not going to diverge, but it's going to go, I don't know, to a value which is 10, it's enough. So there is a question then, okay, given the experiment or given the simulation, is the physics of the slowing down related to all these physics that I'm describing? And this is possible that the answer is yes, even though there is no glass transition. So if you really were able to equilibrate very close to TK, you would see that the point to set length does not diverge. So these are 2 different issues. And then, okay, what are the other things that I didn't have time to cover? So I discussed a lot the p-spin spherical model, and I told you several times that there are many other modern interesting systems. So one of very important progress in recent years is that now we can show that interacting particle system in the limit of infinite dimension have a glass transition exactly like the one that I discussed to you, and that happens for the p-spin spherical model. Okay, so this really say that the intuition of Kirkpatrick thermodynamic waviness is correct. Okay, and so there are techniques that have been developed to do this, and it's very nice, it's important, but I didn't have time to cover it. Then there are, I always try to tell you that there are many. So I can look at the p-spin spherical model because I can study there the rough energy landscape, and the property that I get for the rough energy landscape there actually are common to many other systems. But then, okay, so there is a kind of universality class of rough energy landscape, but it's not the only possible universality class. Okay, so for example, spin glasses behave differently. And this I didn't discuss at all. Okay, And in a certain sense, within mean field theory, you have a little bit, you have these two kind of different universality class concerning the statistical property of the rough energy landscape. And then related to this, there is some topic which is, I mean, very, which grew up in the last years, which is the Gardner transition and the relationship with jamming. Which is, and this, just to tell you very briefly, is actually related to this. So this, what this tells you is that we have studied the landscape, and we have got some property of this landscape. And I started saying, okay, I look at the minima, then I put a little bit of temperature, and this will define my state. But actually, in what has been found studying interacting particle system in very large dimension, is that actually this, here at the bottom of the landscape, you don't have just a very nice minimum, but actually you have a very interesting landscape here that you can see, you can analyze. If you go, let's say, to very low temperature, you take a glass, you go to very low temperature within mean field theory, or especially you go to very high pressure if you take our spheres. And this is why it's related to the jamming transition. So physically, what this means is that if you take your glass, so you know that within the glass you have some local excitation, and these local excitation are coupled. These local excitation live in a disordered background, and since they are coupled in a disordered way, then they can form a spin glass. It's not a spin glass of spins, it's a spin glass of the excitation within the glass. So this is what is the Gardner phase, and that has been studied within mean field theory, and which is really important to study jamming. And I think probably some lectures will discuss this. And then, yeah, I think I'm done. What else I didn't tell you? I think it's enough. I mean, there is a whole, people that try to see whether or not you can describe experiment. They really try to look whether or not let's say, the phenomenology. So let's say there are people that develop scaling arguments to describe, let's say, experiments in simulation. And what I mean by this is that I develop the theory, and I care, a little bit about experiments, so I know how the time scale diverge. But then there are a lot of, let's say, basic fact about the glass transition that a theory should get right. And so you can try to see whether, all this theory get right all this basic fact. And while sometimes you cannot really compute it from the theory, so you do some arguments. And so this, I would say, well, this is done a lot, and then I would put maybe a reference for this if you want to see a little bit more the connection between all this and real phenomena. Okay. So with this, I would like to conclude. So again, my aim with this lecture was to show to you that mean field theory of glasses system really provide new concept, new idea, and new methods to treat rough energy landscapes. So the idea that rough energy landscapes are important in several different fields is something that has been along for a long time. But now it's different in the sense that we have methods and we have techniques to study them. And thanks to this, we can make connection between things which are very different, like problem in computer science and problem in, let's say, condensed matter. And I think this is not something which is finished. There are still a lot of things to find, for example, in biology or also in social science. Okay, so thank you. Yes?
Are you telling us that the theory of spin glasses, this spin glasses, is different from the theory of interacting particles?
Say it again? I say that, so what I say is that spin glasses correspond to p equal to 2, let's say, okay? Ising spins with a two-body interaction. This is a spin glass.
And they have the same theory as interacting particles?
No. So what I'm saying here is that there are two, let's say, roughly speaking, two very different behavior of the energy landscape. One which corresponds to spin glasses, and the other one which corresponds, let's say, to interacting particle. We studied the one which corresponds to interacting particle and which corresponds to p-spin interaction with p larger than 2. Okay? And these two things are very different, even from the phenomenological point of view. If you study the dynamics, really are two different things. Other questions? Yes?
When you use the meaning in the thermodynamics, you start and you count the number of adaptable states, you call that the configuration and entropy. Then you go to real space and you say the glass transition survives, but the states disappear. And then you say the Lexka is 1 over something which you still call the configuration.
Yeah, I mean, maybe I shouldn't call it, but it's the, so the, strictly speaking, is V of QEA. And now the question is whether I can give a meaning to the configuration entropy if I look at the system on finite size, which I think it's possible. But strictly speaking, in my derivation, it's just V of QEA. It will be, I think, the cavity, yeah. Yeah. But in any case, in my derivation is V of QEA, and you can think is the remnant of the configuration entropy within mean field theory. But I think it can be, I mean, it's one way to think about it. I think we discussed this a long time ago, I think, with Francesco. If you look to, if you change the cavity R, and you look, for example, to how the specific heat change, so the specific heat should change abruptly at RC, so you are gaining entropy. And this, the entropy that you are gaining, is the configuration. I mean, it's a practical definition of the configuration entropy. But I mean, again, I don't want to. I mean, as you know, I mean, the definition of the configuration entropy is tricky in finite dimension. But I think it's with the cavity, you can still try to get it in finite. Either you do it on finite size and thermodynamically, or you have to try to do it on finite times.